What is the common ion effect and how does it alter equilibrium calculations in chemistry? In this one page of notes for Unit 7, Topic 12 in AP Chemistry, or in your college-level chemistry course, I'll be defining the common ion effect and bringing back the topic of molar solubility, which I had in a previous video, and then working through an example before and after a common ion is in effect and how it changes the equilibrium concentrations, and that'll prove kind of how we're going to summarize what the common ion effect does. The common ion effect is when we have a slightly soluble salt in these Ksp equilibriums, and the common ion means that when we start out with our products, we have a concentration of one of the ions to start in our initial part of the rice table. Again, we're going to bring back the concept of S, or the molar solubility. Let's just get started with our first example here where we do not have a common ion. So when we have sodium chloride dissolved in water, the dissolution reaction we would write is just sodium chloride solid, one-way arrow because it dissociates completely and it has a very large Ksp. And we make the two ions of sodium and chloride. And what I'm going to do is just show on the particle view, what does that sort of look like, and then compare that to lead chloride and then what happens when there's a common ion. So what it means is there's a lot of sodium ions dissolved in here. I'm not going to really count how many. I'm just going to put a fair amount so that we can compare it to the other two particle views. And then I'm not going to show the water molecules. They would be surrounding all of these ions. The big thing I'm going to do is just make sure I have a chloride ion for every sodium ion and that 1-to-1 mole ratio, okay? And then we would also say that it would reach a precipitate amount, so that just means we've reached the saturation point, but it is a Ksp of 40, which means it's really soluble. All right, how does that look different than our lead chloride? Well, let's first do the calculation. And I did do this calculation in the previous video, but just in case you didn't watch it, let's just kind of run through it again. So we have lead chloride, solid, and then we will do double arrows because this is a slightly soluble salt. And then I'm not going to have room to write the, AQ. And then what we would do is we'd start the problem with no ions of either one, and then we would say plus S and then plus 2S based off of the mole ratio of the equation here. So we get a 2 in front of it. And then I'm going to put the 0 in this time, and then 0 plus 2S. Because when we see the common ion effect, we're not going to have a 0 at the start of our initial concentrations in the table. So then over here, we're going to write the equilibrium expression, which is pretty easy for KSPs. Because this is a solid, we don't have it in the equilibrium expression. We don't solve for the concentration. So it's just going to be the lead ion concentration and then the chloride ion concentration, but squared. So we still have to keep that in effect. And then we put in 1.2 times 10 to the minus fifth. And then we'll put S and then 2S and then squared. And then in the previous video, I solved for what S was. I'm just going to quickly do that in this video. And S ended up being 0.014 molar. So check out the other video I have on 7.11. So that's going to be our concentrations in the table here. So this is going to be 0.014. And then this is going to be 0.028 molar. All right, and that's, again, the concentrations when there's not a common ion effect. So let's just put in 10 lead dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just as long as it's less than the sodium chloride. And then the only thing that's different here is there's going to be 2 chlorides for every lead. So just make sure that you have that shown appropriately. Okay, then we got that one done. So again, that's the KSP and how we'd solve for it without a common ion effect. So I'm going to redo this problem. And the big difference is that this solution right here, in this little particle view, is not just water, it's sodium chloride, or it's salt water. Okay, so what that means is there's already sodiums in there. Okay, so just going to draw a whole bunch of those to start with, just so that you know kind of what's going on, what's different. So that already has a bunch of sodium ions, and then it already has a bunch of chloride ions. So this isn't just water. You're going to put your lead chloride in a salt or a sodium chloride solution at the start. So let's just kind of redo the calculations quick and see mathematically what happens. So again, you have your lead chloride and then double arrows, and then it makes lead ions and 2 chloride ions. So you start the problem basically the same. The only difference is you're going to say I have 0 lead, and then the chloride concentration, now don't get confused, it is 0.1. So when I have sodium chloride and it dissociates, I make a sodium ion and I make a chloride ion. And so this would be 0.1 and this would be 0.1. So don't double it. That's the one thing that students tend to try to do. The concentration of the chloride ions is 0.1 because when it dissociates, we just get the same molarity of the two ions. Okay, then the change is still going to be plus S and plus 2S, but here's the difference. This is going to be 0 plus S, and then this is going to be 0.1 or 0.10 plus 2S in your problem. Okay, so when we go over here, we're still going to use the same Ksp value and write the same equilibrium expression. So we're still going to have the lead ions and then the chloride ions squared, and then that's still going to equal the 1.2 times 10 to the minus fifth. But when we put in here, we're going to put in S, or 0 plus S, but then we're going to put 0.10 plus 2S and then squared. So the calculations change a little bit here. We're going to do something that we've done previously, which is that we're going to assume that this plus 2S is small, okay? Our Ksp value is small right here. And so we're going to assume this, we've done this before with other types of equilibrium reactions. We're just going to assume that it's just a small value, but we still have to solve for S. So what that means is that this is going to end up being simplified, okay, to squared. And then when you solve for S, I'm just going to quickly again do that. You can always do this on your own, get your own, calculator out. But we're going to get 0.0012 molar. Okay, so that's going to be the concentration of here, 0.0012. And then for the other one, it's going to be basically 0.10. Now, if you really wanted to include it, we're going to assume like that's probably with significant figures the correct answer. But if you want to include it in, you would have 0.0 and then 24. But realistically, with significant figures, this would be 0.1 and this would be 0.0012 because they would both have two sig figs here. Okay, so what happened then to our molar solubility, our S value? Well, if you take a peek, the S value went down, okay? And it went down by almost like 10-fold. So I'm going to do to show in the picture, the particle view, is that if the other one had 10-ish lead ions, this one's only going to have one, and then another chloride ion for each one of those leads. But our solubility has drastically decreased, and you can even use Le Chatelier's principle to explain that, meaning we've increased the concentration of a product, so then it's going to what's called shift left. There'll be less of the other product, and then this value will exist based off of the initial value because of the small value for S. And then the most important is we have less lead chloride dissolving. All right, so let's write a summary of what we found out here by doing these calculations. So I'm just going to write this out with you. When lead is added, so when lead chloride is added to and not just water, to a salt, or, salt meaning sodium chloride, to a sodium chloride solution of 0.1 molar versus, you can even write in here, versus just pure water solution, just put SOLN. The molar solubility, we kind of mathematically proved this, molar solubility, that's the S. The molar solubility S goes down, and you could again use Le Chatelier, but really we just mathematically proved that it goes down, and that's because the chloride ion is in common. So that's where they get the name common ion, as a product of the Ksp, equilibrium expression for the lead chloride. And that's because if the concentration of our chloride ions, goes up, it causes the reaction, let's do RxN, reaction to shift left, meaning Le Chatelier principle again, and cause less lead chloride. Now be careful, you might want to make sure you put that lead chloride solid to dissolve. Okay, and you also get less lead chloride ions. So lead chloride ions also go down in concentration or in molarity due to that common ion effect. And that's sort of mathematically we proved it, and now we can kind of visually kind of think through it also with our particle views. All right, so I hope this one page of notes helps you solve what the common ion effect is. I know I did just one problem, but keep in mind this is when there's not a common ion and we get more lead ions to dissolve in solution. But when we do have a common ion effect, meaning the chloride ions are there, they're present at the beginning because we had a salt sodium chloride solution to start with, not pure water. There's less lead ions that will dissolve and more of it will stay as a precipitate in this KSP reaction.